Machine learning technology, the complete AI and ML stack from data and models to MLOps, deep learning, and generative AI. Hello and welcome. In this video, we are going to build a complete mental model of machine learning technology from the ground up. We will cover what machine learning is, how it fits inside the broader AI landscape, what the AI and ML technology stack looks like, which model frameworks matter, how teams build, train, deploy, monitor, and govern models, and why MLOps has become essential for turning experiments into reliable business systems. By the end, you should be able to understand the full life cycle of machine learning, the layers of the modern AI stack, the difference between classical machine learning, deep learning, and generative AI, and the practical trade-offs that shape real-world systems. Let us start with the big picture. Artificial intelligence is the broad field focused on building systems that perform tasks that usually require human intelligence, such as perception, language understanding, reasoning, decision-making, and prediction. Machine learning is a major branch within AI. Instead of writing explicit rules for every scenario, machine learning learns patterns from data. Deep learning is a subfield of machine learning that uses multi-layer neural networks to learn representations automatically from large data sets. Generative AI is a newer application layer that uses powerful models to create content such as text, images, audio, video, software code, and synthetic data. So the relationship is simple. AI is the broad umbrella, machine learning is a core method inside AI. Deep learning is a powerful family inside machine learning, and generative AI is one of the most visible and commercially important application areas built largely on deep learning. Machine learning works by finding patterns in examples. In supervised learning, a model is trained on labeled examples, such as emails marked spam or not spam, or house records paired with sale prices. In unsupervised learning, the data is not labeled, so the system tries to discover structure, such as customer segments or anomalies. In self-supervised learning, the data itself provides the training signal, which has become very important for language and vision foundation models. In reinforcement learning, an agent learns through trial and error by receiving rewards or penalties from an environment. Each of these paradigms has different strengths, data requirements, cost structures, and operational challenges, but together they form the core learning patterns behind most AI systems used today. To understand the industry properly, it helps to think in layers. At the bottom of the AI and ML stack is infrastructure. That includes data centers, cloud platforms, networking, storage, accelerators such as GPUs and TPUs, and increasingly specialized AI chips. Above that sits the compute and runtime layer, including operating systems, container platforms, distributed training tools, compilers, inference runtimes, and orchestration systems. Then comes the data layer, which includes databases, data lakes, data warehouses, streaming pipelines, feature stores, labeling tools, and governance controls. Above the data layer sits the model development layer, where scientists and engineers use libraries and frameworks to train, fine-tune, evaluate, and version models. On top of that sits the MLOps layer, which handles automation, deployment, monitoring, reproducibility, testing, security, model registries, lineage, and compliance. Then comes the model serving and application layer, where models power search, recommendations, copilots, fraud detection, diagnostics, forecasting, optimization, and generative interfaces. Finally, the business and user layer includes workflows, products, APIs, dashboards, and decisions that create actual value. The data layer deserves special attention because machine learning quality is deeply tied to data quality. Data must be collected, cleaned, transformed, labeled where needed, and governed. Training data can come from enterprise systems, sensors, web content, logs, user interactions, transactions, images, medical scans, industrial equipment, public data sets, and synthetic generation. Teams often use batch pipelines for historical data and streaming pipelines for real-time use cases. They also need metadata, schemas, access controls, lineage, retention policies, and privacy safeguards. Feature engineering remains important in many business problems, especially for tabular machine learning. Even in deep learning systems that automate representation learning, data curation, filtering, deduplication, and quality control remain crucial. A strong model with weak data rarely performs well in production. Now let us move to model types. Classical machine learning includes linear regression, logistic regression, decision trees, random forests, gradient boosting, support vector machines, k-nearest neighbors, clustering methods such as k-means, and probabilistic models. These approaches are often fast, interpretable, efficient, and highly effective on structured enterprise data. Deep learning includes neural networks with many layers, such as multi-layer perceptrons, convolutional neural networks for image tasks, recurrent models and sequence models for time series and language, and transformers, which now dominate state-of-the-art language, vision, and multimodal systems. Foundation models are large models trained on broad datasets and adapted to many downstream tasks. Large language models are a type of foundation model specialized for text and increasingly multimodal input and output. The major machine learning framework ecosystem has evolved into a few leading families. Scikit-learn remains one of the most important libraries for classical machine learning, pre-processing, pipelines, model selection, and evaluation. XGBoost, LightGBM, and CatBoost are widely used for high-performance gradient boosting on structured data. TensorFlow helped industrialize large-scale deep learning and remains important in production environments, edge deployment, and some enterprise ecosystems. PyTorch became the dominant research and development framework for deep learning because of its flexibility, Python-first design, and strong community adoption. JAX has gained attention for high-performance numerical computing, research, and scalable model development, especially where automatic differentiation and compiler-driven optimization matter. Around these core frameworks are ecosystems, such as Hugging Face transformers for pre-trained models and fine-tuning, Keras for high-level APIs, ONNX for model portability, and MLflow for lifecycle management. Framework choice depends on the problem, team skills, deployment target, and performance needs. For structured business data, scikit-learn and gradient boosting libraries may be the best starting point because they are fast to train, easy to debug, and often deliver excellent accuracy. For computer vision, natural language processing, speech, and multimodal systems, PyTorch is often the default for experimentation and modern deep learning workflows, while TensorFlow still matters in certain production and mobile or edge pipelines. JAX is valuable for advanced research, efficient transformations, and some large-scale training environments. ONNX plays a different role by providing an interchange format that helps teams move trained models between ecosystems and optimize inference. The most mature organizations rarely think in terms of a single tool. They build a framework strategy aligned to workloads, governance, infrastructure, and deployment environments. Training a model is only one part of the story. The real machine learning lifecycle starts with problem framing. Teams need to define the business objective, the prediction target, the decision point, and the metric that actually matters. Then they collect and prepare data, establish train and test boundaries, select candidate models, tune hyperparameters, evaluate trade-offs, and assess generalization. After that comes deployment, where the model is integrated into applications, APIs, batch jobs, or decision systems. Once deployed, the model must be monitored for accuracy, latency, cost, data drift, concept drift, fairness issues, and security risks. Then comes retraining, rollback planning, change management, and lifecycle retirement. In mature organizations, machine learning is less about isolated training runs and more about operating a living system over time. This is where MLOps becomes essential. MLOps stands for Machine Learning Operations. It extends ideas from DevOps, data engineering, software engineering, and platform engineering into the machine learning lifecycle. The goal is to make model development and deployment repeatable, testable, scalable, and governable. MLOps covers experiment tracking, version control for code and data, model registries, pipeline orchestration, automated testing, continuous integration, continuous delivery, feature management, approval workflows, environment reproducibility, infrastructure as code, observability, and incident response. Without MLOps, many machine learning initiatives stay stuck in notebooks and pilot projects. With strong MLOps, organizations can move from one-off experiments to reliable products that survive real-world traffic, regulation, and business change. A typical MLOps pipeline begins when new data arrives or a retraining trigger fires. Data pipelines validate schema, quality, freshness, and access permissions. Features are generated and stored consistently for both training and serving. A training job starts with versioned code, versioned data, and a defined environment so results are reproducible. Experiments are logged with metrics, parameters, and artifacts. Candidate models are evaluated not just for accuracy, but also for calibration, robustness, bias, explainability, cost, and latency. Approved models are stored in a model registry. Deployment pipelines push models into staging and production, often using canary releases, shadow testing, or blue-green deployment. In production, observability systems track prediction quality, drift, resource usage, and failures. If issues appear, teams can roll back or retrain. This operational discipline is what separates enterprise AI from AI demos. Feature stores became important because many organizations struggled with inconsistency between training and production serving. A feature store provides a managed way to define, compute, share, version, and reuse machine learning features across teams and environments. It often supports both offline features for training and online features for low latency inference. This helps reduce duplication, improve governance, and minimize training serving skew. Alongside feature stores are metadata systems, lineage systems, data catalogs, and model registries. Together, they create traceability. That matters for debugging, audits, compliance, and trust. In regulated industries such as healthcare, finance, or critical infrastructure, the ability to show what data trained a model, when it changed, who approved it, and how it was validated can be as important as the model's raw accuracy. Inference is another major architectural choice. Batch inference is used when predictions can be generated on a schedule, such as overnight demand forecasts, customer scores, or preventive maintenance risk assessments. Online inference is used when predictions must happen in real time, such as fraud checks during a transaction, recommendations while a user is browsing, or conversational responses from a language model. Streaming inference supports event-driven architectures where data arrives continuously from devices, logs, or applications. Teams also choose between centralized cloud inference, edge inference on local devices, and hybrid patterns. The right choice depends on latency, privacy, bandwidth, reliability, and cost. For example, autonomous systems, industrial control, and mobile AI often require local inference, while large foundation models often rely on cloud-scale serving infrastructure. When people talk about layers in the AI stack, the most discussed layer today is generative AI, but it should be understood as part of a broader architecture. Generative AI systems usually include a pre-trained foundation model, a fine-tuning or adaptation strategy, an orchestration layer, tools or retrieval components, safety controls, and an application interface. A large language model on its own is not a complete enterprise solution. Real systems need prompt management, grounding, retrieval-augmented generation, context assembly, vector search, policy enforcement, output filtering, evaluation, observability, and cost controls. In other words, generative AI adds a new interaction paradigm, but it still depends on classic machine learning disciplines, software engineering, infrastructure engineering, and governance. Deep learning sits underneath much of modern AI progress because neural networks can learn hierarchical representations from raw or lightly processed data. In computer vision, lower layers may learn edges and textures, while higher layers learn objects and scenes. In language models, earlier components represent tokens and local context, while deeper layers capture broader semantic patterns and long-range dependencies. Transformers change the field by using attention mechanisms that scale well and handle context effectively. That shift enabled breakthroughs in translation, search, summarization, coding assistance, image generation, speech synthesis, and multimodal reasoning. However, deep learning comes with high compute cost, significant energy use, larger data demands, and lower interpretability than many classical methods. The best model is not always the biggest model. The best model is the one that fits the problem, constraints, and risk profile. Evaluation in machine learning is often misunderstood. Accuracy alone is rarely enough. For classification, teams may track precision, recall, F1 score, ROC-AUC, calibration, and confusion matrices. For regression, common metrics include mean absolute error, root mean squared error, and business-specific tolerances. Ranking systems look at metrics such as NDCG and mean reciprocal rank. Generative AI requires broader evaluation, including helpfulness, factuality, toxicity, hallucination rate, grounding quality, latency, and cost per response. Human evaluation also matters, especially when user trust, safety, brand impact, or domain expertise are involved. Offline evaluation is useful, but online evaluation such as A/B testing or shadow testing often reveals production realities that benchmark scores miss. Good machine learning teams align metrics with outcomes. Responsible AI and governance are now core parts of the machine learning stack, not optional extras. Models can amplify bias present in data, create unfair outcomes, leak sensitive information, generate harmful content, or fail in unexpected ways when conditions change. Governance includes access control, auditability, risk classification, documentation, model cards, data sheets, testing protocols, human oversight, security reviews, privacy protections, and incident handling. There is also a growing need to comply with regulations, sector-specific rules, and internal policies. Security for AI systems spans the full pipeline, including data poisoning, prompt injection, model theft, adversarial inputs, and supply chain risk in open source components and pre-trained models. High-performing AI without governance can create legal, ethical, and operational problems that outweigh its value. The business impact of machine learning is broad because prediction and pattern recognition are foundational capabilities. In healthcare, machine learning supports imaging analysis, triage assistance, drug discovery, clinical operations, and predictive risk scoring, though it must be used carefully and under strong oversight. In finance, it powers fraud detection, underwriting support, risk modeling, anti-money laundering, customer intelligence, and algorithmic decision support. In manufacturing, it helps with quality inspection, predictive maintenance, supply chain forecasting, and process optimization. In retail and media, it improves recommendations, demand planning, pricing, marketing personalization, and content understanding. In software, it enables co-pilots, search, automation, anomaly detection, and user support. Across industries, the real value usually comes from embedding models into workflows where decisions, automation, and human action can improve outcomes. One of the most important practical lessons is that not every AI problem needs deep learning or generative AI. For many tabular problems, gradient boosting and well-curated features remain hard to beat. For highly regulated environments, simpler and more explainable models may be preferable. For low latency or low power use cases, smaller models and edge deployment may be necessary. For enterprise knowledge tasks, a retrieval-based generative AI architecture may outperform blind fine-tuning. For highly dynamic environments, online learning or more frequent retraining may matter more than model complexity. In other words, machine learning architecture is an exercise in trade-offs. Teams must balance accuracy, interpretability, latency, cost, scalability, governance, maintainability, and user trust. There is no single best stack for every organization. To bring everything together, the modern AI and machine learning stack can be understood as a layered system. Infrastructure provides compute and storage. Data systems collect, govern, and transform information. Frameworks and libraries enable model development. Classical machine learning, deep learning, and generative AI offer different modeling approaches for different kinds of problems. MLOps turns these approaches into repeatable production systems through automation, monitoring, versioning, and governance. Applications then turn predictions and generated outputs into real-world value. The organizations that succeed with machine learning are usually not the ones with the most hype. They are the ones that connect data, models, operations, people, and policy into a disciplined system. Thank you for watching, and I hope this gave you a clear and practical map of machine learning technology, model frameworks, MLOps, and the full AI and ML stack.